Hey everyone, welcome back to the channel. The Internet Protocol is used in computer networking to transmit data packets between hosts on the Internet, and this protocol operates at the network layer of the OSI model, providing reliable and connectionless service for the transmission of data. IP packets consist of two main components, the IP header and the data header. And in this video, we're going to focus on the IP header for a moment and discuss the various fields and how they work together to enable the delivery of IP packets across the Internet. The version header, as it indicates, identifies the version of the Internet Protocol used inside the packet. And the value of the version protocol can be either 4 for IPv4 or 6 for IPv6. And the version header is essential for routers and other networking devices to identify and correctly process IP packets that have different versions. And this is important because the different versions of IP are not backwards compatible. If a router only supports IPv4 and an IPv6 packet is sent to it, because it doesn't support that version, it will just simply discard that packet. The length header is used to indicate the length of the IP packet, and it's necessary because the IP header can include optional fields that increase the overall length of the IPv4 header. And this allows the receiver to locate the start of the data payload regardless of the presence or absence of these optional fields. And this is necessary for routers and other networking devices to locate and interpret the various fields in the IP header accurately. The value of the header is a field that's multiplied by 4 to determine the actual length of the header in bytes. So, for example, if you had a header length of 5, that indicates that the length in bytes is 20 because 5 times 4 is 20. And this has a minimum value of 5 and a maximum value of 15. The type of service header is used to indicate the priority of the packet and to enable quality of service features. There are three subfields, which are the precedence, delay, and throughput. Precedence is used to prioritize packets with different levels of importance. Delay is used to prioritize packets that require low latency, like a voice call, and throughput is used to indicate the amount of network resources that a packet requires. And this ensures that critical traffic is given priority over less important traffic, which improves the overall network performance. The total length header specifies the total length of an IP packet, including the header and data payload in bytes, and it allows the receiver to know the exact size of the packet so that it can allocate enough memory to store it. If the total length of the packet exceeds the maximum transmission unit on a network link, the packet will need to be fragmented before transmission. Network devices use the total length header to determine the size of the IP packet and how it should be handled. The identification header is used to uniquely identify a fragmented packet and to allow the receiver to reassemble the fragments back into the original packet. When a packet is fragmented, the identification field is copied into each one of the fragments, and the receiver then uses this field to identify which fragments belong to the same packet and to reassemble the fragments in the correct order. This field is important for ensuring that the fragmented packets can be properly reassembled and delivered to the correct destination. The flags header is used to control the fragmentation of the packet and indicates whether additional fragments are present. And there are three flags: the reserved bit, the don't fragment bit, and the more fragments bit. The reserved bit is unused and that's set to 0. The don't fragment bit is used to indicate whether the packet can be fragmented at all. So if this bit is set and the packet exceeds the maximum transmission unit of the network, the packet will be dropped and an error message will be returned to the sender. The more fragments bit is used to indicate whether additional fragments are present. And if this bit is set to 1, there's more fragments after the current one, but if it's set to 0, then the current fragment is the last one. And it's important for controlling the fragmentation of a packet and ensuring that all fragments are properly reassembled at the receiver. The fragment offset header is used to indicate the position of a fragment relative to the original packet. When a packet is fragmented, each fragment includes the fragment offset value, which indicates its position in the original packet. And by comparing the identification and the fragment offset values of incoming packets, the receiving device can determine which fragments belong to which packet and in what order they should be reassembled. The time to live header represents the maximum number of hops that an IP packet can take before it gets discarded. The initial value of the header is set by the sending device, and it typically ranges from 64 to 128. And every time that a router or a network device forwards an IP packet, it decrements that value by 1. And if the value reaches 0, the packet is discarded and a time exceeded ICMP message is sent back to the original sender. So this header is designed to prevent packets from looping indefinitely within a network. The protocol header is used to identify the protocol in the data payload of the packet. And most commonly, this is going to be a 6 for TCP or a 17 for UDP. This value is set by the sender, and the receiving node uses this field to identify the protocol used in the payload of the packet and forward it to the appropriate protocol handler for further processing. The checksum header is used to detect errors in an IP header during transmission. The header checksum field contains a value that is computed over the entire IP header using an algorithm. The header field is calculated by the sender of the packet before transmission and verified by the receiver upon receipt. So if the checksum value computed by the receiving device does not match the value inside the header, the packet is assumed to have been corrupted during transmission and it's dropped. The source IP header enables the receiver to identify the source of the packet and to send a response back. The sender will set the source IP address to its own IP address before sending the packet, and the source IP is represented in dotted decimal notation, which means that it consists of 4 numbers between 0 and 255, all of them separated by periods. And the source IP can either be a public IP or a private IP. The destination IP header identifies the recipient of the packet on the network, and this allows routers to forward packets to the correct destination and for recipients to identify if a packet belongs to them. And just like the source IP header, it's represented in dotted decimal notation and can either be a public or a private IP address. The option header is a variable length header that can be up to 40 bytes long, and it can be used to provide additional information or instructions to routers that are handling the packet. Options are only included in the header if they're necessary for the delivery of the packet or if they're requested by an application. This is rarely used in practice and is typically reserved for a specialized application that requires a specific handling. The data header contains the actual data being transmitted between the sender and the receiver, and this is a variable length header that can contain up to 65,535 bytes of data. The format and structure of the payload depends on the protocols that are being used by the application. For example, TCP can be used to transmit data between applications, whereas ICMP may use this for error reporting and diagnostic messaging. Here's a visual representation of the IPv4 headers and their size, and to summarize, the version indicates the IP version being used, the header length specifies the length of the IP packet, the type of service provides information about the priority requirements of the packet, total length indicates the total size of the packet, including the header and the data, identification uniquely identifies each IP packet to help with the reassembly of fragmented packets, flags provides information about packet fragmentation and reassembly, fragment offset indicates the position of the current fragment in the original unfragmented packet. Time to live specifies the number of hops that a packet can travel before being discarded. Protocol specifies the transport layer protocol being used. Checksum helps ensure the integrity of the IP header. Source IP address specifies the sender. Destination IP specifies the recipient. Options provides additional information about the packet. And data contains the payload of the packet, which is typically an upper layer protocol data. I hope you found this video informative and helpful in understanding the different headers in an IP packet. Each header contains important information that is crucial in routing and delivering packets across the internet, and understanding how these headers work is essential for network administration and for troubleshooting. If you have any questions about what was covered, please leave a comment below. And if you enjoy these tutorials and you want to support my work, please like this video and share it with others. If you have the means, you can contribute to my Patreon or leave a tip in my jar. Be sure to subscribe to stay updated to my latest content, and thank you all for watching.